There are three things I want to talk about. They're all optimization questions from 14.7. And then we'll start on our last section, which is also about optimization, but it's using a different technique. So there are three questions. One of them is, I'm calling it a number problem. It's to deal with picking three numbers where some property is true and you're trying to optimize something. The second group of questions are like 12, 13, and 14, where you're trying to optimize a box. By that, you're trying to find a box with the maximum volume or the minimum surface area, whatever it's going to be. And the third question is, you're trying to find either the point or the shortest distance from a point to a given surface. So that's the three basic ones. Now, what I want to do is just set up the question so that it looks like just what yesterday was about. You know, it's just, here's a function, you know, find its critical numbers and so on. So find three positive numbers. This is similar to question 11. Find three positive numbers whose sum is 80 and whose product is a maximum. So what we're trying to do here is we're trying to maximize a function. I'm going to call it x, y, z. All right, so we're going to try and maximize that. And the jargon that we use is, given that the three positive numbers always add up to 80. So that's essentially what that looks like in mathematics. So you've got a function that's the product, so it's x, y, and z, but you've been given this. So what I'm going to do is you're going to take this thing. It's very often called the constraint. So I'm going to take the constraint and I'm going to rearrange it so that it tells me what z is in terms of x and y. I then go to this function here, which I'm going to now call g of xy, and it's going to be x times y times z. And if I multiply that out, that's your goal. Your goal is to find a function and two variables that look like this. This function here represents the product, but you notice now it's only in terms of x and y instead of x, y, and z. We know from yesterday how to find out its absolute max and absolute min, right? Don't you just differentiate it? You know, what am I going to call it? dg by dx, I guess I could do that line. So you're going to solve, right, you're going to solve that, and you probably get a couple of answers, but the answer you're interested in is the one that gives you a maximum, right? And by that I mean the one that gives you a maximum x, y, z. And anybody got any gut feelings for what that magic number is going to be? Any ideas what x, y, and z? Basically just using symmetry. What's your gut feeling for what it could be?
The cube root.
Oh, cube root. Very interesting. I wasn't thinking that. Oh. I think I know where that's coming from. Go the other direction. Would you agree that by symmetry, x, y, and z are equally important? And so by symmetry, it seems reasonable that they should all be the same number, whatever that number is. And since these three things must add up to 80, does it not make each one of them has to be a third of 80? That would be my gut feeling, and I'm pretty sure it's right. I kind of like the cube root one because that's coming later. There's a different question where that would have been the correct solution. But nonetheless, you're going to find it, and this is the guy that you're going to use. So in each of these questions, we are going to find an optimization function. And once you get to there, treat it like yesterday. Just do the same thing, solve for local max and min. Some optimization functions, you're trying to find the biggest answer it could be, but in other ones, you're trying to find the smallest. Okay, next question. This one involves 11, 12, and 13. This one I'm going to do is like question 14. And I'm just reading it off the screen here. And it says, find the dimensions of a box with the largest volume if its total surface area is 120 square meters. So I will have a function which is its volume function. And so that's x, y, z. Actually not unlike question 11. And I am being told that its total surface area is 120. So it might be worth visualizing what that could look like. If I call this x, I call this y, and I call that z. If you're told that the surface area has to be 120, then you need to find the surface area of this box. Although it's a pretty badly drawn box, 2xy, 2xz, 2yz. Okay, let's see if hopefully you can see what I'm doing here. See if you take this guy here and this guy up here. This box is basically made up of 6 sides, isn't it? Left, right, front, back, top, bottom. And this is the front back combination. Do you see that's an XZ and that's an XZ? So that's where that 2XZ is. So are you comfortable with the total surface area is this? Now this guy is the constraint. And this is the guy that you will rearrange to get Z equals. And once you've rearranged this to get Z equals, you put it in here, and that's you got your guy that you're going to be using for the rest of the day. So I got to figure out algebraically how that's going to work. So I'll take it slowly. I'm going to just subtract 2xy from both sides. Remember, the goal here is to get Z on its own. So that seems a reasonable first step. What do you think should be my next step?
Factor out a Z, the Z.
Thank you. Corrected yourself in time there. And lastly?
Divide both sides by 2x plus 2y.
Now, you don't need to do this next step, but I think it just makes life easier if the numbers are smaller, right? It's not absolutely necessary that you do that, but yeah, every little bit helps. Which means now that this fella up here, right, the volume function, which I'm now going to call gxy, is x, y, z.
Shouldn't it be 60 minus xy?
Thank you.
Thank you. That's why I have students, to keep me on the straight and narrow. I'll rewrite that again because it is a bit messy. I would probably do this, although I'm not sure if it's a great help. That is one ugly looking function. Aren't you going to have to do its partial derivative with respect to x and then its partial derivative with respect to y? And set them equal to 0 and try and find some x's and y's, right? Try and find some critical numbers. One of those critical numbers will be the x, the y, and the z that you're looking for. Now, if I look at this function, do you see it's symmetric? You agree? Wouldn't the clue be here that if it is symmetric, then shouldn't the x, the y, and the z all be the same number? Because they're all equally likely to be in any given position. And so my gut feeling here is that when you do the solution to this question, you'll find that the x, the y, and the z will be the same number. Now, I can't guarantee what that number is because it's kind of mixed up in here, and that's not so obvious. But it does exist. And that is the process for finding the dimensions, that's x, y, and z, of the box with the given surface area. Be really careful here in these questions. Sometimes they ask you for the dimensions of the box, in which case your answer will be, you know, x is 5, y is 2, z is 18, you know, whatever it really is. And sometimes they just say, what's the volume of the largest box? So yeah, you do find x, y, and z, but you multiply them together and the answer is just a single number. So just read carefully, because sometimes they want to know the dimensions. So there's 3 numbers, right? X, comma, y, comma, z. And sometimes they just want to know what the maximum volume is, which means it's a single number that you get by multiplying those 3, in this case, those 3 together. Are we good? Right. Now, finding a shortest distance from a point to a surface, I believe that's, where the heck is that? There's at least 1, if not 2 questions that do that. Let me find out what their numbers are. Yeah, so one of them is question 9 and the other one is question 10. So let's do a version of 10. Find the point on the plane x take away y plus z equals 4 that is closest to the point 1, 2, 3. Can I kind of visualize this? Imagine that there's a point 1, 2, 3. There's a point up here called P, whose coordinates are 1, 2, 3. And somewhere over here, there's that plane. Right? I mean, it's not just a rectangle, you know. Planes go on forever, right? But you can't really draw forever. Can you imagine that there is some point here, I'm going to call it Q, that is the shortest distance from that plane to the point P. Does that seem reasonable? There should be such a point.
Yeah.
And it's unique, at least in the geometry of this situation, Reggie. There's only one place where that would work. If you moved a little bit higher up, wouldn't it be longer? If you moved a little bit left, it would be longer, a little bit to the left or the right. No matter how you move around Q, everybody else is just a little bit bigger, a little bit further away. So we kind of know what we're after here. What we have to do here is create a optimization function. So what I'm going to do is create a function that is the distance from P to Q. Right, that's the guy I'm trying to minimize, right? A formula that uses only X's and Y's that gives you the distance from P to Q. So far, so good. Now, what do I know about the coordinates of P? Well, they're nice. What do I know about the coordinates of Q? Well, right now I don't know anything, so I'm going to call it that. And isn't the distance from P to Q X take away 1 squared, Y take away 2 squared, Z take away 3 squared? Do you remember the distance formula in 3D? Because that's what I've just used.
I remember that it existed.
Okay, you now remember because I've told you what it is for future reference. Now, I need this thing, right? I guess I should start thinking about how this is going to get changed. But don't I need this weird, ugly square root stuff to only have X's and Y's in it so that we can do yesterday's work? And it looks like I've used everything up. But there's one piece of information I haven't used yet that is going to allow me to turn this Z, because it's the only place where there is a Z, into X's and Y's. What is that piece of information that I'm going to use?
Before.
Agreed? Now, if I take the fact that since Q is on the plane, that this is true, doesn't that make Z that guy? So what I now have is that the distance from P to Q is the square root of 1 minus x squared plus 1 y minus 2 squared plus Z take away 3, right? Z take away 3, which is that guy. Now, this is the optimization function. But before you get too frightened here and think, oh God, that is going to be a real pain to differentiate, I'm going to use some logic here. If you square the distance, then you get this expression. And the argument goes something like this. If this thing is the biggest answer, won't this be the same biggest answer? In other words, whatever point makes this the largest will be the same point that makes the square root. If a number is really big, won't its square root be the biggest it could be? Does that logic make sense, that we can use this as our optimization? And the reason I want to use this is, would you agree this is much easier to deal with as far as calculus is concerned? So this guy here, this is the guy that you are going to do partial derivative with x equals partial derivative with y equals 0. You're going to get a whole load of critical numbers, hopefully not too many. And one of those critical numbers will be a maximum, right? One of those critical numbers will be a maximum. And the X, the Y, and the Z that give you that, that's the guy that you're trying to find. That is Q. Now, I'm going to cheat here and pretend I know the answer, which I don't. But let's just say, for argument's sake, that we find out when X is 5 and when Y is 3, you get a minimum value, right? You get the smallest answer. The question says, find the point on the plane. Well, I only know 2 of them, but I need the coordinates of all 3. Where am I going to get the third coordinate?
Put it into the equation for the plane.
Probably this version here, because it's easiest to use. And making this up, you get 10. So when you do that question, you're going to have this equation or something similar. You're going to do the usual solve for when this is true. You'll probably get, I don't know, it's hard to judge. You might only get 2 critical numbers, you might get 4, but one of those 2 or 4 will give you the smallest answer. And when you know who that guy is, figure out who Z is and call it good. Does that process seem okay? Do you understand, although I haven't finished it, how you're going to finish it? Now, be careful on these questions. If they ask you to find the point, this is what you want. If they ask you to find the shortest distance to this plane, you won't just find this point. Won't you plug it into here, the untouched square root guy, and come up with the answer is it's square root of 27, or whatever it might end up being. So again, just first sentence typically, find out if you want a coordinate of a point, or find out if you want a single number, right? Find out if you want the dimensions of the cube, that's X, Y, and Z, or do they just want to know the volume of the cube, which is 42? Because it'd be a pity if you did all the hard work and then just screwed up because you told them a coordinate when they wanted a distance, or you told them a distance when they wanted a coordinate. Any questions about those guys? Because puzzle questions, in this case optimization ones, tend to cause the most trouble. We're good? Right, well, we still have officer. Well, maybe today, but certainly officer tomorrow when you have a more time to go and look at it. So what I'm going to do now, hold on a second. We're going to get set up for our next section. Is there anything I should know? Good, Jacob can hear me. Where am I going with this? Close this window, open that window. I have so many blinking windows, it's not true. All right, yeah. Okay, got myself finally organized. Here we are. Lagrange, keep calling him. I don't know why I keep calling him. But we're going to look at Lagrange multipliers and optimization. And
is Lagrange French?
Yes, unfortunately. The French, if you look at the history of math, you'll find out that, I don't know why it happens, it just kind of happens, that there are periods in time when mathematics explodes, the knowledge and the information and whatever you want to call it explodes. And it tends to happen in little bursts, and then things go quiet for a while. Right now, mathematics is really, really quiet. There's not that much, wow, new cool stuff, right? And when these explosions happen, for another weird reason, they tend to happen in quite short locations. So for instance, the French were really, really cutting edge mathematicians in the 1700s. They were pumping out some really cool stuff, right? And this guy here, Pascal, a whole load of other people, really, really top-notch guys. Leibniz and Riemann, Germany, they had a bubble where for about a generation they were pumping out some really cool math. Newton, Green, Simpsons, Maclaurin. There was a point in time where they were pumping out a whole load of really brand new cutting edge math. And I don't know if it's luck or whatever, but it seemed to happen in a very localized place, right? And for instance, way further back, the Italians at the time, where they were turning out some really good mathematicians. Now, it only needs to be 3 or 4 really good mathematicians, but they all feed off each other. And they give each other ideas, and then they use their ideas with someone else's idea, and then they build something even bigger. Fascinating thing. So this is part of that explosion where the French were doing their thing. So Raynaud, Pascal, L'Hopital, who was Belgian, but we'll call him French, they were in that chunk of time. Okay, so what is this thing called Lagrange multiplier? Well, it's used to optimize functions with a constraint, which is kind of what we just did, whatever it was, 25 minutes ago. But they do it in a totally different way. So let's show you how it works by just doing a question. What one will I pick? God, there's tons here. I should start. Let's start simple. Suppose you have a function x squared minus y squared, right? And we're being asked to find what are called their extreme values, which I would say find their max and min, right? Find their maximum and minimum. Given this constraint. Now, in this particular question, the constraint is that x squared plus y squared equals 36. So I'm trying to find the biggest answer that this can be, but only using values of x and y where this is true. And I'm trying to find the smallest answer that this can be, and only using values of x and y where this is true. So can you imagine that that's quite a difficult problem, right? How do you actually solve that kind of question? And this thing called Lagrange multipliers is how you do it. And what they found out was, if you solve that equation, you will find the solution to where is this a maximum and where is this a minimum. And it says the gradient of f is equal to lambda times the gradient of g. So you thought you'd seen the end of gradient, didn't you? Nah, gradients appear later on in another totally different situation. So gradients kind of hang around there. Okay, now that has to be true, and this fella here, right? This one here is normally your second thing. So you're going to solve when is the gradient of f equal to lambda the gradient of g, and that this needs to be true. Now, this guy here kicks in at the end. So I want you to imagine that we solve this and we get 3 or 4 candidates, right? 1, 2, 5, 7, 3, 3, that kind of thing. Well, for all the candidates that this generates, you use this guy and you keep the ones that work and you kick out the ones that don't work. And the ones that work, right, the ones that make this true, they're the guys that are going to be your problem. They're going to be the solution to your problem. So let's show you the process. The gradient of f, lambda the gradient of j. Right, now the gradient of f is what? 2x negative 2y. And it's going to be lambda. And the gradient of j is going to be 2x and 2y. Think of that guy there as being your g, right? Now I would rewrite this as a system of equations. Oh, that was an ugly way of writing, a bit too late now. So here is, in this case, here are our three equations. And we're going to solve these a very, very specific way. So in one sense, that's good, right? Now, if you go looking on the internet, you will find other techniques, other ways of doing this. And if you don't like the way I'm doing it, feel totally free to go and look at some videos and see other approaches to the same problem. All of us end up with the same correct answer. So it's not like I'll do it and you'll get one answer and somebody else will do it a different way and it's a totally different answer, right? There's only one answer and we're all going to get there. So this is my technique. Step one. Assume that lambda could be 0 and check for usable solutions. Now, if I tell you that lambda is 0, you know, this is bugging me. I'm going to have to fix it. Yeah, I mean, it's the same thing, but here we go. If you make lambda 0 here, doesn't equation 1 just become 2x equals nothing? Doesn't equation 2 become negative 2y equals nothing? And doesn't equation 3 become x squared plus y squared equals 36? Now let's solve. Would you agree that x has to equal 0, y has to equal 0? Does that work for equation 3? So, no good. But you have to check for it, because I tell you, for every 10 questions, 9 of them, it's no good. The one you don't check is the one where it gave you a solution that worked. Right, so it's going to be that Murphy's Law thing that you're going to get tired and say, why am I bother checking this? None of them ever work. And you're right, none of them virtually ever work. But there's always going to be an exception, isn't there? There's always going to be one, oh, I wasn't expecting that. That one actually works. Right, so you have to do the check because there's no way to tell whether this is going to be the rare situation where this solution actually is a usable one, right? So that was step 1. Step 2. Assume lambda is now not equal to 0 because we've already tested it for 0. So we're now going to say, we're going to test it for all the other situations where lambda is not 0. And then do this. Take equation 1 and divide it by equation 2. Well, let's see what that looks like. Equation 1 divided by equation 2 should equal equation 1 divided by equation 2. Now, if you do this correctly, the lambdas will cancel each other out. and probably quite a lot of other things as well. And can you see in this case, you get x over negative y, and you get x over y. Just a side point. Why must I assume that lambda is not equal to 0? Why must I assume that in this particular context?
Because
So
you divide by 0.
Yeah, it's to avoid the dreaded accidentally dividing by 0 problem, right? Now, if you rearrange this, you get xy equals negative xy. And if you combine them, you get 2xy equals 0. And that is not bad news. In fact, there's not too many things that can harm here. So let's go hunting for solutions. Isn't one solution that x should be 0? Would you agree that would work in this context? X equals 0 would work. Now, if x equals 0, question? Now, I'm only making one of them 0. So watch what happens here. If you then put that into equation 3, which is that x squared plus y squared equals 36, won't 0 squared plus y squared equals 36? And won't that get you plus or minus 6? So here are some solutions. 0, 6 and 0, negative 6. Won't they do work? What's another possibility from here that I haven't used yet?
Y equals 0.
And can I save some time and money and whatever? If you make y equals 0, can you trust me that you eventually get these two answers? Does that seem reasonable? So haven't we found the 4 and only 4 critical numbers in the universe that work for this puzzle? So which one of them, or sometimes you can have 2 or 3 or even all 4 of them, but which one of these, right? What were they asking in this question, answer? Let me find out again. Oh, they're looking for the maximum and the minimum, so they're wanting both, right? So I would probably go something like this. 0, 6, 0, negative 6, 6, 0, negative 6, 0. And for every single one of them, I will find the value of x squared take away y squared. Okay, if you plug 0, 6 in, you get that number. If you plug 0, negative 6 in, you get that number. If you plug 6, 0 in, you get this number. And negative 6, 0, you get this number. So that tells me that these two guys give you the minimum, and these two guys give you the maximum. And in the box that you're meant to be doing your answer in, it looks something like this: maximum value and minimum value. Well, the maximum value was 36 and the minimum was negative 36. So in this case, they don't want to know the coordinates of where it happened, just what the final value is. So if you take this function, but you're only allowed to use x's and y's where this is true, the biggest answer that this will ever be is positive 36. And if you're interested, it happens here and here.
So
and
they give us the given constraint?
Oh, yes.
Okay.
Part of the question is this. The question and the constraint. You need both of the question is...
So I was a little confused on the g of x is equal to 36 and like how you got the g part.
Oh, well, I just took this equation, right? And I basically, anything with x's and y's count. You could, if you were being a little bit more of a purist, and I've seen this in some textbooks, that they make g of x the whole thing. I don't think it matters because aren't the partial derivatives in both these cases the same?
Yeah, and then
So-
the function where lambda is entered, where it's the partial derivative of g, that's because the g is the given constraint.
Yes.
Okay, awesome. Thank you.
Are we good on that one? So essentially, I should have put a number on this. Step 3. Step 3 is where you go hunting for solutions, right? And getting the max and mins. Are we good with that?
I think so.
Now, if you are trying to imagine visually what that might look like, it might look something like this. Can you imagine that you were doing a sketch of x squared minus y squared? What the heck does that look like? I think that's a cone. Don't quote me on that. It's a cone. Probably isn't a cone, too late now. Well, let's do that. Suppose you had a cone, and suppose the constraint was the x plus 2y equals 2 or something. Can you imagine that you take this thing and you cut it with a plane, like a z equals thing, plane? What you would end up is a kind of curve that's on the surface, kind of a diagonal ellipse. And can you imagine that guy would be the max and that guy would be its minimum? So can you imagine the surface being cut with a plane of some sort? In this case, oh, that would be a cylinder, so it'd go up the way, right? And you'd have a max and you'd get a min. And if that visually helps. Actually, go to Gizmo 3D Calc and put them in if you need to visualize it. But the key to this is the 1, 2, 3 step. If you can follow that kind of shopping list, things normally work reasonably well. So I'm going to see if I can find a more difficult version. Yeah, I guess you can only do what you got. So here we go. And this one is similar to question 4. Oh, good grief. Forget that. I just looked at the time. I wouldn't get it done. Okay. So tomorrow, all day tomorrow, Lagrange. While I'm doing all my chatting here, say hi. Your test is definitely going to be on Tuesday. And you already know that the test is going to be everything up to and including this, which is basically chapter 14, right? But only the stuff that we've done. Homework is due on Sunday, midnight. Okay. Anyone else?
No class Monday, right?
Good point. No class Monday. It's a holiday, Martin Luther King Day. And
the test is from 8 to 10.
yes. And the test is 8 to 10. Does that all work for you? You're all comfortable with that? You know what's happening? Okay. Test will appear on WebAssign. I just realized that I haven't done anything about how you upload your working. So I'll try and remember to show you what you need to do. If you've had me before, then you know what to do, but most of you haven't. Your working is vital for this. Otherwise, you could just simply cheat, use some software, find out the answers 42 and just type it in. So I want to see your working, so that's for the non-cheating. I want to see you during the test so I can make sure your big sister's not behind you telling you what to do. And the plus is WebAssign just gives you virtually 0 or 100%. But if I see you're working and it's 90% right, and there's a little plus 2x that disappeared, or it turned into a minus 2x, and therefore your answer isn't quite perfect, you still get virtually all the points, right? So you get a lot more partial credit points than you ever would if you just left WebAssign to do yes and no on you. So there is pluses to showing where you're working. Any questions? If not, we'll call it a day.